Mm-hmm. Good morning, everybody. Welcome to this amazing talk, dear students, researchers, science enthusiasts. We are the network of researchers on the chemical emergence of life. NoRCEL. NoRCEL was inaugurated in 2013 and based on in the UK and Leeds. We are pleased to present you the talk entitled Exploring Dark Molecular Clouds, the Cradle of Life's Building Blocks. It will be also available via Zoom. Everybody welcome who are in online. For the first time, NoRCEL founder Dr. Sohan Jeeta will come to Mexico for 2 days of academic and student talks. The invitation to the other talk will be given tomorrow at the Instituto de Investigaciones Biomédicas at UNAM. Tomorrow's talk will be only presential, face-to-face. This presentation will explore how dark molecular clouds, such as the Horsehead Nebula, serve as prolific chemical factories capable of producing complex organic molecules under extreme conditions. These molecules may have been delivered to early Earth through comets and meteorites, playing a pivotal role in life's chemical origins. We look forward to your participation as we explore the molecular origins of life. Please.
Gracias, Miriam. Y como nuestra colega Miriam del Instituto de Investigaciones Biomédicas nos había señalado, bueno, pues esta es una reunión de los distintos grupos contenidos también en NoRCEL, que participamos activamente en los estudios de química prebiótica, y a mí me gustaría presentar una biografía corta del doctor Sohan Jeeta. El doctor Sohan Jeeta tiene un doctorado en química prebiótica experimental, es fundador también del grupo Network of Researchers on the Chemical Evolution of Life, NoRCEL, que la doctora Miriam Palacios Pérez de Biomédicas ya nos platicó un poco de este grupo. El doctor Jeeta es presidente de los siguientes grupos científicos también: Frontiers of Sciences, Blue Earth Project, Latin American Hub, Astroscience Exploration Network, Microbial World Network. Tiene aproximadamente más de 40 publicaciones. Es un miembro activo del Instituto de Física de Inglaterra, de la Royal Society of Chemistry y the European Astrobiological Network Association and the Royal Microscopical Society, y también es Fellow de la Royal Society of Biology. Vamos a presentar entonces al doctor Sohan Jeeta. Le damos la más cordial bienvenida a nuestra universidad y a nuestro instituto. Va a presentarnos entonces explorando las nubes moleculares, cuna de las moléculas prebióticas. Entonces, muchísimas gracias. Bienvenido, doctor Sohan Jeeta. Muchas gracias por estar aquí en este espacio también del Instituto de Ciencias Nucleares. Mi nombre es Alejandro Heredia Barbero, soy investigador titular de este instituto y también miembro y vicepresidente de NoRCEL. Thank you very much, and please go ahead with your presentation. Thank you very much for accepting our invitation to be here.
Yeah, thank you very much, Alejandro. I'd like to thank Alejandro and Miriam for this invitation. Actually, it's been wonderful to be here and to the university, and okay, it's wonderful to be here in relation to having some discussion on various chemicals in space, and it'll become apparent what I'm talking about in a minute. But before I do anything else, what I really want to do is to tell you something about this new conference coming up, and this is Astroscience Exploration Network, and it's going to take place in connection with the NASRDA, NASRDA. This is the equivalent of ESA, the European Space Agency, or NASA, and we're actually collaborating with these guys and delivering Science education program type of a presentation in Nigeria. It's going to be both live and online as well. I hope you're able to do either one of them. We'd love to have you there. So let's move on because time's running out. Sorry for starting late. And of course, we've got this title here, Exploring Dark Molecular Clouds and the Cradle of Life's Building Blocks. And as my name is Sohan Jeeta, I'm founder and chairman of NoRCEL, Network for Researchers on Chemical Emergence of Life. And let's move on. So, in this presentation, I will illustrate life's building blocks perspective using the solid phase chemistry taking place on the surface of interstellar dust particles. It'll all become clear in a minute, everything, but let's move on. Let's see what we got here. So I'm going to talk about small molecules a little bit. There's a reason for that. The reason being is this, that for life to have merged and then evolved probably required something like 100 to 150 small organic molecules. So what do I mean by small organic molecules? Well, to be quite honest, I consider any molecule to be small, which is monomer. For example, adenine. What's happened? Adenine, for example, adenine being one of the nuclear bases used in biology. It is a complex molecule. It's made up of 3 elements. And as you can see, also got aromatic compounds as well. Its aromatic rings are here as well. Whereas next one, phenylalanine, is made up of 4 compounds altogether: oxygen, hydrogen, carbon, here, nitrogen here. And it's also got a ring here, so it's complex. And the reason, I'll come back to that actually, the next bit I was about to say, but that's what I mean by small. But also, a lot of people don't know this. These polysaccharides are made up of smaller, for example, glucose, hexose, you see? Those are made up of formaldehyde, and those are the monomers of sugars. So bear that in mind. So sugars were made from formaldehyde. And as it frozen, oops. Right, here's an example of more small monomers. These are the example of monomers. There's about 60 monomers here. I'd like to draw your attention to amino acids. These are 13 amino acids. Altogether used in biology, present-day biology, it's 20 amino acids. In literature, I could only find 13 amino acids. Oops, what's happened? So in biology, only 13 amino acids are used. 20, but I could only find 13 in literature. These were the amino acids probably used by biology when it started on planet Earth. And I'm going to talk about where were they made, molecules first, before I concentrate on science, the astroscience. The Titan here, this is atmosphere of Titan. So as you can see, this is haze here. This haze sitting on top this less dense. So within these two, you have trapped molecules, various molecules, and these molecules would be radiated by cosmic rays, like gamma rays, and for example, X-rays, and also UV light from the sun, and particle radiation from the Titan's host planet, Saturn. And those particles within the magnetosphere of Saturn will be having effect on these trapped organic compound in this layer. And of course, it'll break bonds, then reform bonds, and then it'll rain onto the surface of the Earth. A lot of people seem to think that there is life on Titan. This is simply because there is what's called methane on that celestial body. But the thing is that methane's been around ever since the moon was made. But the question arises, well, why is the methane still there? It should have been destroyed by now, something like 4.3 billion years after it's being present on the surface of Titan. So it should have been destroyed, but it hasn't been destroyed. It's still there, some of it, but what's it doing there? Where's it coming from? A lot of people seem to think that there are methanol present on the surface, which are continually generating methane, but methane getting continually being destroyed by the radiations I mentioned. And so that's why people think that there's life, but I doubt very much. But anyway, there's new research coming up. I haven't fully updated myself on that, but I will be on my next presentations that I do on this in this area. And the next one we can move up to is lightning. Lightning within plumes of volcanoes. There are two types of lightning: the one that occurs on deserts, and there's one that occurs within the smoke of volcanoes. The volcano lightning is much stronger than the one that's over desert, which is less intense. And so the molecules within these plumes, for example, like carbon dioxide, monoxide, sulfur dioxide, sulfuric acid, hydrochloric acid, methane, you get all of these gases. And also there's a soot coming out of the volcanoes as well. All of these lend themselves to form new molecules. So they rain back onto the surface of the Earth, and people seem to think that this may have started the emergence of life on the planet Earth. Then there is hydrothermal vents. So as you know, that Earth was formed something like 4.7 billion years ago, about 3 to 4 billion years after the crust was formed. This crust would have had plate tectonics. Within the plate tectonics, you would have had some sort of a kind of a volcano, like black smokers and white smokers in these hydrothermal vents. And but I doubt very much, that's my opinion, but of course a lot of other scientists would disagree with me that, because this requires a little bit more time than just to form a crust, but it also requires some sort of continent movement. My friends who work in this area, they insist that that's the case, but I insist it is not the case. But that's why I put a question mark after the hydrothermal vents in the ancient seas. And then we can move on to small puddles of water. I haven't got a picture here showing it to you. There is actually a white smokers. I should backstep now a little. There are white smokers. These are the ones where the life actually people seem to think has started. They usually occur about 1 kilometer away from the black smokers, which is what we have on our present day Earth. Black smokers are something like 450 centigrade temperature, which is really too high, and it's also acidic. Highly acidic for life to have begun. in this black smoker. So white smoker are much more friendly, biology friendly. So temperature is usually something, we're friends here, we can say 80 centigrade plus or minus 10. And also it's alkaline, as opposed to being acidic. And people seem to think that this is where it took place. So this is to do with the hydrothermal. I'm talking about events, vents, not events, vents. So the next one, I'll go back to the puddles of water on the surface at the foot of volcanoes generally. And as you know that they have to be near the volcano, these puddles of water, because tiny little veins coming through the, bringing oxygen, all the gases through these bubbling into these small puddles. And people seem to think that molecules were made like this, and that went on to make life. And then finally, impactors. Impactors such as meteorite, comets, and asteroids. These impactors actually generate a huge amount of energy when they hit Earth. And as a meteorite hurtling towards the Earth, head of the asteroid would be heat up to in excess of 2,000 centigrades. So any molecules present in the asteroids or in the meteorite or comets, they would have been one, they would have been evaporated. Two, bonds of these organic molecules within it, they would have broken bonds and reformed, and then people seem to have think that these might have been instrumental. By the time it hits the Earth, the energy cannot be measured in any humanly conceivable way. Like, for example, you measure it in terms of nuclear warheads. How many nuclear warheads does it take? These objects generate in excess of hundreds of tons of energies generated by these, and you can imagine they can generate heat and other shock waves. They would have broken bonds. Those organic molecules on the surface of the Earth, as well as those were in the comets themselves, impactors themselves, and they would have broken bonds and reformed, and then people seem to think that molecules were made in that way and would have been delivered onto the life would have started then. But of course, there are other ways as well, and one way is astrochemistry. And let's talk about astrochemistry because that's my special subject. So Gilmore and Shefton wrote a book in 2003 entitled An Introduction to Astrobiology. They reckon that something like 1.6 centimeter to 1.6 meter thick layer was formed all the way around the whole of the Earth with these organic molecules. And from this, I can surmise that 95% of the life's building blocks or the organics would have actually started the emergence of life. The chemistry taking place in the sense of astrochemistry is phenomenally more compared to all the other the ways that forming I mentioned in the previous slides. So I think it's highly probable all the molecules were generated via astrochemistry. But that don't actually really denies that there wouldn't be any molecules formed according to the previous slides. There could have been, but majority of them what high chance that it was astrochemistry that brought about the emergence of life on planet Earth. So let's move on now. So space is not empty, and you got structures like these. These are called dark molecular clouds. And they're also known as dense cloud, because it becomes clear in the next slide why are they called dense clouds. And so space isn't empty. And also these things are contained within places called interstellar medium. So they're within a interstellar medium. So here's you got Eagle Nebula. Nebula is just a fancy name for a cloud, and technical name, in fact. And within that, you have these pillars of creation nebulas. So just so you know, that a bit of terminology I was giving you before I moved on to the next bit. So although Barnard 68 looks dark here, you can see that there appears to be nothing. And Herschel, in his days, he said there were holes in sky. And when he looked at it in his telescope, of course, these photographs are taking really, really sophisticated cameras and huge telescopes. But in his days, they had a big telescope, in that, according to their time, of course, but they were only looking with their eyes. With your eyes, you would only see black and white. So it's no wonder that Herschel called it holes in the sky. But we now know that in Barnard 68, it's not true, because if you take photograph with infrared camera, lo and behold, what you see is see through it. You see these thousands of stars beyond it, beyond Barnard 68 nebula. And so I'll start moving on towards the chemistry. And here's a Orion constellation of Orion. And I do know that in this country, it would be seen as is presented here. But in the next slide, overlay, I should say, it's not slide, overlay. I'll show you how it looks like in Ecuador, because I've seen it. But I have taken a photograph in Australia. I did astrophotography in Australia. My camera wasn't still strong enough to discern colorful, wonderful, like the Betelgeuse here, orange, and Rigel here. And if I move it on, it gives you more stars in that region. Here they are. And it was unable to discern these wonderful colors. But still, you need a lot more sophisticated technology, and sometimes you need a different filters in order to see it. So you might use to see red. You will use red filter to see the red light coming from a star. So in the olden days, that's what they did. They used various filters in order to make a composite of image. What you're seeing, I've seen this Horsehead Nebula. Here it is. I've seen this and with a 4-5-inch telescope, and of course I could only see it black and white. Just so you know. And I'll come back to this. Oh, here's the next slide. This is what you see in Ecuador on the equator, and normally I ask a question like, what would it look like in Australia? Anybody want to have a guess? What would this Orion would look like? Here's your Betelgeuse, here's your Rigel. So where would the Betelgeuse be? Just to tell you a little bit upside down altogether. So Betelgeuse would be here, where the pointer is now, and Rigel would be where Betelgeuse was. And this is the Orion sword. It'll be pointing up rather than sideways here. Of course, it was down, pointing down in the previous overlay. Okay, let's talk more about these Horsehead nebula and what makes them special for chemistry. These Horsehead nebulas are actually radiated by particle radiation, as written here, atomic hydrogen, you got proton, you got deuterium plus, and then alpha rays and so on. And you've got also radiated by our electromagnetic radiation, EM, electromagnetic radiation. In particular, UV light. But I should let you know that really particle radiation has energy generated in the region of 50 to 100 giga electron volts. Electron volts is one way of measuring, not just, it's like joules. Joules is a weird number. I can't go into that because in the interest of time, but if you compare the two units exactly the same, you'd end up speaking about electron volts rather than talking about joules. Another one thing, although I said used EM radiation, but strictly is not true. But I like to have categorize as particle radiation and electromagnetic radiation, making them two distinct way of doing it. But that's not strictly true, because gamma ray and X-rays, they actually really knock out the deep set molecules in atoms or in the electrons within these various chemicals. And bring about the, I'll talk to you about that later in a minute, right? Rather than get bogged down here. They're made of 80% molecular hydrogen, and so although I called it dark molecular clouds, of course, they're also called dense clouds as well. Dark because they are dark, they look dark like this in a general, but if you take photograph in special way, you'll see that they're not really dark in a minute, which is next overlay. And of course, so molecular, when we use the word molecular, we're talking about two hydrogen atoms, the gas, we're talking about H2, that's what we say molecular. Of course, you would also say dihydrogen, which also means the same thing. So I prefer to call dark molecular clouds instead of dense clouds. So both terminology is correct. And helium is at 19% within these that's the second most element present in the universe. First one being hydrogen, and the second one being helium. By the way, you know, more often than not, we interchange this word hydrogen. We have to make it clear for people, what do we mean by hydrogen? So chemists would, when they talk about hydrogen, they would be either talking in terms of dihydrogen, or they'd be talking about molecular hydrogen. But to you and I, we would say, I breathe oxygen. That's the same comparison with hydrogen. We're actually talking about molecular hydrogen. But of course, when chemists talk about it, they say hydrogen to mean atomic hydrogen, H, just a symbol HO with this new one proton and electron written like so. And so just so you know, the terminology is being used here. And of course, 80 plus 19 makes it 99. The other one, 1%, is not even 1%, it's less than 1% actually, are other heavier elements within these clouds. For IDP stands for interstellar dust particle. For every million 10 to the 6, that is, million dihydrogen molecule per cubic centimeter, there is one interstellar dust particle. And it is this that the presence of interstellar dust particle that makes it dark, like so. And you might say, well, there's so much hydrogen, only one in cubic centimeter. If you take a cubic centimeter, space, and all of that space, only one interstellar dust particle, why isn't it see-through? Well, it is sort of. You will see it in the next bit, what I'm about to show you. But the point I'm to make here, I'm trying to emphasize that it is dark because this is in three-dimensional everything. It's not flat everything. So we don't know how deep this Horsehead Nebula is. With all these centimeters of coming in front of you, these interstellar dust particle gives it a sort of darkness, like so. But let's have a look if that's true. Look, if you take it with infrared camera, this is what you see. Now you see in its glory the Horsehead Nebula, and you can see that the darkness has actually become slightly less, sort of, is not so opaque now. And this star here is beyond the Horsehead Nebula on the other side. And this silver lining, what we call silver lining here, this is where the UV light acts, because UV light does not penetrate at the heart of these nebulae. What penetrates are two things only: particle radiation, gamma rays, and X-rays. So those are the ones that carries out the chemistry deep within these Horsehead Nebula. And pressure in these places is something like 10 to the minus 13 millibar. Of course, I don't know what convention you follow. Probability is that you follow the Americans. They use the word torr. We don't, in Europe, use the word torr. You can convert it very easy, to be quite honest. Millibar is, I understand millibar, then I understand torrs. But the figures are very, very similar in both of these, because I've been brought up with using millibar as a unit of measurement for pressure. And so this is very, very low. Generally at this point, when I'm not doing online, I also explain how small this number is. This number, we cannot conceive this number, It's inconceivable. This number is so small. It's incredible. But still, chemistry occurs. And this pressure is important when I come to talk about the gas phase chemistry, which is not going to talk about, but I'm going to highlight the problems with that. And temperature in these places is something like 10 to 50 K. Of course, there are papers that says 10 to 100 K. But there are a few of those. There are more of paper that writes 10 to 50 K. So pick your choice. I mean, everybody defends their own science, as is the case with all of us, all scientists, all the scientists all over the world. And so I'll move on from here. And here's the real McCoy. This is the real interstellar dust particle. This was brought back by Stardust mission. You can see these sort of tubes here, these bubbly sort of these things. Someone did a calculation, actually some scientists did a calculation, that it forms I think you'd understand soccer pitch. It's soccer pitch, the area, these convoluted in these interstellar dust particle, and this surface lends itself for doing serious astrochemistry on that surface. So size, football pitch size. This is 0.1 micron. in size altogether. And generally, the less than 0 micron is old-fashioned unit. Of course, modern-day unit is micrometers. And they're made up of 80% silicate and the rest being carbonaceous materials. That is organic materials we're talking about. And the water is the most stickiest molecule in the universe. If you go home tonight and you go into your fridge, into the ice box and pick up an ice, and you find that it sticks to your finger. This is because it is very, very sticky, and the stickiness is because of the lone pair of electrons that it has. And that what makes it sticky. And the molecule I'm talking about, of water molecule I'm talking about here, by the way. So it sticks to the surface of these interstellar dust particles and forms what we call icy mantle. It's just a fancy way of saying icy. Or by the way, this interstellar dust particle here, it's not like the one that you ski on. Not that kind, not the time that you get it out of your icebox in fridge. It's actually a bit like woolly. We say amorphous. People just want to be funny about these things, but anyway, it's a bit woolly. It's kind of amorphous. It has no shape. It's irregular shape, you could say. All right. So 25% of the chemistry occurs on the surface of these, and the rest being other 75% is gas phase. I'm not expert on gas phase chemistry simply because I still don't understand it. You know, as the pressure falls, right, or the volume gets larger, and because these clouds the nebulae actually don't have boundaries, and they actually molecules move apart, and so with fall in temperature, molecules actually would come closer, but during a shock wave, for example, from a local star or supernovae and novae. These shock waves would throw these molecules apart. And then you'd say, well, so here's one molecule. Say this laser is one molecule, and it splits into two particles, two ions, two radicals, whatever you want to call them. But how do they get back together if they're far apart? You know, it's a bit obscure to my mind, and I don't understand it. I'm perfectly happy living my life with solid phase chemistry, if you understand what I've just said. All right, here's sort of a more diagrammatically, this is my version of interstellar dust particle. So the white layer on the outside, that's the icy mantle. And as I said, you get all these molecules kind of impinging on it. And they stick to it. They stick to the ice very, very quickly, forming a layer and dissolving it as well, sort of. I mean, another layer of a molecule would be onto it, so they'll be sort of in the middle, I'm trying to say, and as well as on the surface. I shouldn't have used the word dissolve, because there isn't water. It's to do with 3 point about water itself. So also, here's some electromagnetic radiation. It impinges on it. So here you'll be talking about the gamma rays and X-rays. And of course, here's on this side I've shown particle radiation impinging on it, breaking all these bonds. And once they reform like formic acid would be coming off. And formaldehyde will be coming off. And there'll be atomic hydrogen about as well in space, going towards the icy mantle and absorbing onto it, onto the surface. One of the unknown questions to date actually is, and if you found it, we know what the universe is if you know the answer. And you've probably be known more than Einstein, Newton, Galileo, Darwin. I mean, for the entirety of life's longevity of Earth, people will remember you. We don't know how dihydrogen is formed. This is simply because after about 300,000 years of universe inflation, not Big Bang, inflation. We don't use the word Big Bang, we talk about inflation nowadays. So basically, after 300,000, you'd only have electrons and protons around, and electrons and protons could easily get together because it would have been, everything would have been sort of closer. But once they form atomic hydrogen, that is a neutral particle, which is hydrogen with its one electron. Question becomes, how do the two hydrogens get together? The thing is this: when you sort of bring them together, and I need to draw energy diagram in order to show it. Actually, I might do it for the next talk. I will put an overlay on this to show energy diagram. That if you bring the two atoms of hydrogen together, so as you come nearer and nearer, the energy builds up between these two. Once they touch one another, in order to exchange the energy, bring the electrons into the common orbit, it actually explodes apart immediately. And that energy splits the hydrogen from being formed, a dihydrogen being formed, I'm talking about, okay? And in the present day, our present day knowledge of this formation is called three-body reaction. It was discovered by Chapman in the 1930s, British scientist. And so you have two hydrogen coming together, and they kind of move along towards one another. As soon as they touch one another, they form dihydrogen. Any energy generated would be absorbed by something like this interstellar dust particle here, and you call this three-body reactions. But there were no interstellar dust particles some 300,000 years after the big inflation of the universe, you know. So you could actually say, well, how did that happen? And one explanation that's given nowadays is that it's to do with tunneling. Well, that's what's happening, but it still doesn't explain how was it that it was done then. Tunneling, I assume, happens on some surface. It doesn't happen like, here's two hydrogen, there's tunneling going on, you know? So I've no idea. They don't know what the idea is. Nobody knows. You guys can discover it. And of course, a lot of the other chemistry that's occurring at the same time is this during shock wave, you know, the icy mantle would be melted slightly, and the movement of new radical formed would come together, forming better chemistry. So here's what's going on the surface of the ice. So these are ices here, both of these are ices on the right-hand side. And the top left box is to do with the photons, UV photons. That's another way of writing. We simply, sometimes we say UV photon, other times we say UV light. Same difference. And so as I explained to UV light, actually, only does damage on the surface of, in this case, it'll be interstellar dust particle. But of course, these interstellar dust particles would have been present on in the silver lining of the dark molecular cloud, what I was talking to you about earlier on. And whereas here, in energetic particle, they can go deeper into the ice. And what they really do is to knock out the deep set electrons within the molecules that formed ice. It's not just the ice, it's the other absorbed molecules within the icy mantle. And these electrons that are knocked out deep set, they go on to do the damage elsewhere. What I should have done actually is kind of formed another line here, or another line coming in this direction, about there. And only to show that electrons are moving about in the ice, and they actually make chemistry happen. Electrons carry high energy, as you know. It'll be an excited state, these electrons. And generally speaking, the energy that's serious chemistry occurs within something like 5 kilo electron volt. That's the type of energy you need. Less is better. Anything above that is sort of a suspect, you know. It doesn't happen much. And so that's the energy formation, the molecule formation on the surface of dark molecular clouds, interstellar dust particles. So here you have, just showing sort of childish clouds, just to show you all of these are you could say kind of where UV light is active, and whereas this dark here interior of this UV light may not reach, and therefore no chemistry. But of course, the particle radiation would reach. And you know that that's happening because Aurora Borealis, they're the one is example of particle radiation coming into the atmosphere, Earth's atmosphere. And well, how do you know there's evidence in space? Very, very quickly. I hope somebody's keeping time for me. So Murchison meteorite is one example. Quickly, here's the burgundy colored spot there. That's a chondrial. Within these you'd find that if you take a drill and you gently grind into it, very gently, not like this. This is simply because drill will generate a heat. It will break the bonds on some molecules, and thereby doing its own chemistry. So that's not real chemistry. And so you do it gently and produce some powder. You put the powder in pestle and mortar, and then you grind it. I should have said mortar and pestle. So you grind it. Also, you add acetone to it. All the organics will dissolve in acetones, and that will go on to. If you do HPLC on it, high performance liquid chromatography, nowadays you can get 3-dimensional HPLC as well, really sophisticated apparatus. And they can tease out even the hidden molecules within a molecule, within a curve. And you can actually turn this such that there'll be another curve behind the main curve to show you that other molecules are formed. So the modern HPLCs are really sophisticated. And to date, we have discovered a huge number of compounds in these, including the 5 nucleic acids used in biology on Earth. Only 17, by the way, I have it known, only 13, only 13 amino acids, as I pointed out much earlier on. And then you get something like this. This is radio telescope measurements for this antenna, And you pointed out dark molecular clouds such as Horsehead Nebula, and then you tweak it to certain wave numbers. Wave number is just a fancy way of saying frequency, just reciprocal, the two things are. And wavelength, I should say. So they're just reciprocal of one another. So in this case, for example, carbon dioxide has a wave number of the ones where I'm not going to read them out in the interest of time. And also it will produce a trace like this shown here. And you can see all of these molecules being produced, as well as carbon-13, present in far off structures such as the Horsehead Nebula. And of course, how do you know that they're happening? Well, this is an example of carbon dioxide. Carbon dioxide actually vibrates, like if I do with my arms like so, it'll vibrate. And every time energy impinges on my arms, it actually contract. So my body would be carbon, my fists would be the oxygen, it will contract. This is the excited state of carbon dioxide. Of course, if I asked you to stand on one leg, you will not be able to stand on one leg forever and a day. You'd have to emit some of this energy. So they do emit some of this energy, and it goes to ground state. And the energy emitted are in these wave numbers for carbon dioxide. And these are the ones that this radio telescope picks up, and as well as, of course, you'd also. So let's talk about just a quick sentence on these wave numbers and so on. Each molecule produces different wave numbers. Okay, each molecule is to do with a functional group. So if you have, for example, here's a methanol. Can you see there's methanol here? It will have a different wave numbers. And ammonia would have a completely different one. And so what I'm actually trying to say is that something like, say, aspartic acid, it has both alcohol, that is OH, and acidic, COOH molecule, and as well as it'll have CH3, methyl group as well. So all of these would have a different numbers, wave numbers. And to decipher them is very, very difficult. So you really have to tune it sensibly. You can't just point it out, measure everything. You just will not be able to decipher anything. But you really do have to have a bit of expertise, know-how behind to find these things, what the molecules are. Of course, then you will tally up with chemistry being in the lab, which is this gray diagram showing, and this is what I will be concentrating on. Before I do that, let me tell you about the Stardust space mission here between 1999 and 2006. This is the one that went to the Wild to fly by Anne Frank comets as well. So what happens is that, like if the sun, if this my laser here is traveling this direction, and the sun my fist is the sun is traveling, and what it would do is that all the volatiles and the interstellar dust particle would actually be dislodged, and it'll produce a comes, or tail, as we say. And in the spacecraft Stardust went to visit this Wild 2. I know it's written Wild. I think this is Dutch scientist. He liked to be called Wild, as I understand. And so basically, it went through the commie, and out popped the gel on a pottery dish. Well, of course, pottery dish is not in the sense of like it made of plastic or glass. It'll be steel one, like a cap sort of. It opened up, and as it went through it, it scanned, had all the particles impinging on it, and we found that was the particle I showed you, the one on the earlier slides. It was because of this mission here, they found that what it was like. And we also found on that interval about dust particle, there was a glycine amino acid. This is the first of the 20 amino acids used by biology on Earth. So now I'm going to start talking about the astrochemistry part of it. I'm not, what I'm going to do, I go through this very quickly, just to show that how these you've got the wave numbers on the coming molecules coming on the surface of the interstellar dust particle, and then you've got these wave numbers would be appearing here. It will be round bracket what's being measured. So here it is, guys and girls. So here's the original Gibbs diagram, what they measured. So here you go. So you got water being top one, right? And then you got ammonia, methane, carbon dioxide, carbon monoxide. I was giving a talk in Western Turkey University about 4 days ago, this same talk. I said, well, I don't know what the wave number is for this is OCS, it's carbonyl sulfide, yeah? But I don't know the wave number. He said, I should have actually cut to that guy and asked him, hey, what is it? Because I don't know. He did mumble something, but obviously I missed my opportunity to find out about that. What's the wave number for it? I can't seem to find it. So then you have methanol and finally OCN here. And up until recent times, we did not know what this X was. Here it is, where the question mark is. Question mark is. We didn't know where, is that it? Yeah, anyway, the point is we don't know what it is. Well, we called it XCN. You know, we do these silly things. We kind of, if we don't know something, we put an X. You know, the airports all over the world, the older names, like I can only remember the British Birmingham in Britain. Airport was called BM, Birmingham. BM was the original initials. So in order to conform with the international standard, which was made sometime in the 70s, so what they did was to put an X after that. I think JFK is another one, but I don't know how that goes. But there are many, I think Bombay may be like that as well. So they put an X there. So we put, as a scientist, we put X's everywhere. What we don't understand, put an X, come back to it. And of course, we know that X to be O for oxygen. And it's called cyanide. And that its wave number is 2165. If you tune your infrared Fourier transform to it, and you'll lo and behold, we'll get a peak, and I will have that peak, and you'd love that peak. And so let's move on quickly. Here's again trying to form what's called ammonium carbamate, zwitterion. Zwitterion, somebody did not know what zwitterion are. They're sort of two component molecules, right? Instead of being held by a bond, they're just held by a charge. In this case, that's why it's called zwitter. I think it's the name of a guy, by the way. There's a positive charge here. I think I put a, yeah. I should have swapped it around, but you know where this is going, held by positive negative charge. That's all you need to understand. So to prove it, it consumed some amino acids, formic acid, and so there's shown here formation of formic acid. Here's hydrogen being formed from ammonia, irradiation of ammonia in the presence of carbon dioxide. You get a formic acid. And I don't want to go through it in the interest of time. But the thing is about this, you compare this one with the Frasco's 1964 trace, you find that it pretty well matches it. So you know that is formic acid, ammonium carbamate, and it's a Zwitter ion. And this is again talking about that three-body reaction. I don't want to go through that either because I will talk to you about it. And this doesn't work, so I know that. I don't know what's wrong. I made a video on it. But these are the type of apparatus you use, but I'm not going to describe these in the interest of time. I'd rather you have get the better understanding of chemistry rather than me babbling on about how it can be done. If you want it, you can ask me afterwards. So this trace, these are the kind of results you get. This is taken by Fourier infrared transform spectrometer. And the pink trace, I'm only showing a pink trace here, is of carbon dioxide and ammonia, 1-to-1 mixture. And let's see what happens. These are the vibrations modes you find. So you got, for example, carbon dioxide or carbon monoxide. There are two vibration modes, so it's given here 2V2 and plus V3. They're just a fancy way of labeling these things, you know, these peaks. And so going to the next one, this is pre-irradiation, this is clear. And now, this is still pre-irradiation. These are peaks for ammonia. These, this, now we see that it's post-irradiation, and the black curve is post-irradiation. We do the same comparison again. These are the carbon dioxide, these are the ammonia. Here's a new peak, right? And that peak is composed of a cyanide, the one that I talked about much earlier, and carbon monoxide. And here, over 300 organic molecules have been identified to date, and the reason is slow pace that these identification taking place. As I said earlier on, that it's to do with the functional group each molecule has, and they make spectrums really, really complex. And you do experiment like this, and you correlate these results with those that are obtained by astronomers with the radio telescopes. So what I'm doing here, oh, what happened there? I jumped the gun, never mind. So I'm simply here, what I'm actually doing is to comparing what Gibb has found in that trace, and this is the, by the way, I turned this upside down so that it's with mine. So that's why these wavelengths, they measured it in the wavelength, it's nm micrometers, micro mm, right? So it's upside down. Here's XCN here, right? And so let's see what goes on here. And this is just to show you that the two laboratory experiments do tally up with what you see in space. And okay, let me now fully explain this. Why does OCN at 58, this is turquoise, the minutes of radiation, compared to this here pink one, 58 minutes, you'd think it would be more. So OCN curve should be here above it. But it's not actually, it's less. Why is it less? And so it's because, it's because of, it's being broken down. It's being broken down into carbon monoxide, because carbon monoxide, look, it's less here, OCN. It goes all to the top. It surpasses, way surpasses turquoise here at 17 minutes. And so you know that OCN is being broken down. And okay, let's move it forward and see what's going on here. So what you can do, one thing that we did do is to measure area using origin package. These are Gaussian curves, you can measure them. And rather than math, you can do it by hand as well, but it's better to get a package that does it quickly. And you can measure this here, and you draw this. And the energy is the time of radiation here, and the area under the band. And you find that the black is the carbon monoxide is increasing, and the OCN at certain point is start to decrease. You remember I told you it's broken down. It's broken down into carbon dioxide and nitrogen gas. You can't see nitrogen gas because it's called a homonuclear. In other words, you cannot detect its vibrations because the moment charge is the same all over. And you have to use a special way of finding that out, like, for example, mass spectrometer experiment to find that out. But the point of people have done that. We know that that's nitrogen there, and OCN converts it to carbon monoxide plus 2 electrons, whereas the blue one stays the same. It's just to give you a sense that there is some chemistry taking place. There are some changes going on, you know. And let's move on further. And so, but if I go back, if you were to add these two curves, yeah, if you were to add the carbon monoxide and this, let's see what happens. Oh yeah, that's right. That's what I'm saying here. If you add red and black curve here, and lo and behold, you get this green one here, carbon monoxide, just to show you that the carbon monoxide was coming from the destruction of carbon dioxide, OCN. That was the only objective here to show you what's going on. And okay, so you know that look at these curves for ammonium ion, they're increasing steadily, and therefore it's thought about some point. Can you see that they get narrower with one another? At some point, they become stable. That's just to prove that what's happening to destruction of ammonia into ammonium ion. And this is to show you you know, I'm so sorry, I've forgotten. This is just to remind you about the formation of zwitterite, that's all. But I can't say any more about that, actually. Anyway, let's move on. I've only got 2 slides left. So this one is to do with we're comparing radiolysis, the particle radiolysis experiment here, and using carbon methanol. So we get chemistry. We're doing radiolysis again, using ammonium and methanol, you get organic chemistry. Using photolysis, that'll be UV light. And photolysis of methanol, again, you get the chemistry. And you got somebody called Ferris, and he measured the tail of component chemicals in a comet's tail, and you observed some chemistry in those as well. Then precursor on IDP, precursors on the IDP, that will be the modeling. And you can see that modeling shows chemistry does takes place on the surface of IDPs. And this is just revisiting, just reminding you about takes place on the surface of an interstellar dust particle, and we found glycine amino acid. And I think that, sorry, let me just explain this as well. So radiolysis and things like that, that's to do with the last guy I talked about, the IDP, what's going on IDPs. And here we're comparing experiment done by a guy called Milaruri back in 1953. They irradiated gas of ammonium, water, hydrogen, methane. And they got some chemistry, so he measured these are the amino acids that came out of that. It wasn't as many as this, but this was when the results were re-examined in 2007 after his death, and that's what you got actually here. And of course, it's comparing Uri Miller's experiment with those found in protein found on Earth in proteins. So these are the common amino acids here. And these are the ones that found in meteorites as well. So you know that the biology did deliver some amino acids. They did get somehow incorporated into our biology. Proof is here, in this here, found in these two, Uri Miller and this. And if you compare the previous results as well. And so what we got is conclusion. So I'm actually done with just to prove that chemistry is rich and it could occur and it would have been instrumental onto the surface of the Earth. Of course, all of those molecules would have been delivered by impactors. Thank you very much, everyone. Any question?
Dr. Sohan Jeeta, thank you very much for your nice talk. And let's go for the comments and questions. Do you have some questions here in this auditorium? Well, Mario, go ahead.
First of all, thank you very much for the talk. It was very interesting, and also it brought an integrative view of the astrophysical, all the astrochemical point of view of the prebiotic chemistry. And I just wanted to ask you about this specific term of the amorphous water in the surface of the dust particles.
Yeah.
So are we talking about liquid water or some kind of ice that's amorphous like a silicate?
There is no liquid in space. There is no liquid whatsoever. What you would find in space would be molecules floating about, water molecules, single water molecule floating about. And if they happen to be in the vicinity of interstellar dust particle, it would get attracted to it and they'll attach to the interstellar dust particle, yeah. But there's no water ever. There is a certain bit might occur when there's a shock wave coming from a nearby supernova. These shock waves would actually, I think even then they would have quickly I don't want to use the word melted it, sort of in the process of I can't seem to say that word. Yeah, thanks. Yeah. So basically during that, because they're close to one another, they become slightly looser. So molecules actually move towards one another, and the radical especially, and they will reform into different molecules. Because you know that that's happening because of the laboratory experiment dictates it. Yeah, it happens in laboratory.
Okay, thank you very much.
Muchísimas gracias. Thank you very much. Who else? Okay, Brian.
Thank you, Doctor. Is there, I don't know, to your knowledge, is there any kind of limit of the complexity a molecule could achieve in interstellar space? I mean, there's a lot of energetic processes that can break molecules, but if there's a limit, because I remember some years ago that we found like a 20 long peptide inside a comet, no? Something that we never thought could be happened. So is there a limit? You could conceive a limit on that?
No, it's not. I mean, you know, it's oyster is your world. You know, it could be any number of. There could be. But it's the matter of sort of detecting them. More often than not, they occur in a particular part of the curve on these traces. And that particular, I can't remember the wave number that it happens at. And we think that that's where more complex molecules would be formed. This is what the panspermia hypothesis people jump onto, saying that's where it's happening. But on the whole, you know, you can detect some longer molecules, but they're generally chains of carbon. Yeah, most complex things we've ever detected are the nucleobases, and we should be thankful, because the aromatic rings are difficult to detect. They're complex. Each bit in that ring would produce some sort of signal, yeah, complex signal, and you have to tally that up what you see in the laboratory experiment in order to confirm what's happened. But of course, they identified these nucleobases in meteorites, so you know that these things are happening. So the whole thing is not just the radio telescope measurements, it's not just what's happening in the laboratory, but it's also what people see in meteorites that gives you the whole picture of chemistry in space. But more than about 300 molecules, we don't have a bigger picture, you know?
Thank you.
So that's it.
Thank you, Brian. Do you want to ask something else? ¿Alguien tiene alguna otra pregunta, some comments, algún comentario? Well, let's see the questions and comments here in the chat. Adrian says tryptophan is another amino acid. And Eduardo, thank you very much. Thank you very much for sharing your knowledge with us, with all of us. Here's my question. Thinking in terms of molecular evolution, what are your thoughts on nature's apparent preference for producing only L amino acids in the proteins of living organisms?
What we need to understand is we need to understand proteins. To use the word protein is a complex because proteins are biology made. We need to be talking about polypeptide and peptides. There are definitions like, for example, oligopeptides, and these are usually about 10 amino acids long, and which means that that fits in with the remit of 13 amino acids, what I identified, which means that these amino acids could have been instrumental in the emergence of life. In particular, two, aspartic acid and glutamic acid, it has both carboxylic group as well as hydroxyl group. So these are generally, these two amino acids are generally been found in protein where the active site, enzyme active sites are. Those are the instrumental, and the other 7 may not have been important. So we only need some small peptide in the oligomers region to get some sort of chemistry going on planet Earth, you know. So yeah, that's all I can say on that, you know, because I've not written all of this up, but I will one of these days, you know. Yeah.
Very complex question, by the way.
Yeah.
Adrian says, the typical density of a gas in these clouds, it's around millions to thousands of millions of atoms per cubic meter. Earth atmosphere has around 10 to the 25 per cubic meter. Interesting that biological amino acids are of the L isoform, but deoxyribose, the sugar in DNA, exists as the isoform in nature. Then Adrian says again, astronomical measure molecular emissions from molecular clouds, such as methanol, can be observed in different transitions, including 6.7 gigahertz, 12.2 gigahertz, and well, another frequencies. Okay, and that's it. We have no more comments or questions in the chat. And do we have more questions or comments here? ¿Tenemos más preguntas o comentarios aquí?
Just to read about the one about the measuring 10 to the 25, because I'll have something to say on that.
Go ahead, please.
Just read it out. Read out again.
The typical density of a gas in these clouds is around 10 to 6 to 10 to 9 atoms per cubic meter.
It's not 10 to 6. It's not. It's not. But you can actually work out Boltzmann's equation, because if you know the temperature and you know the Boltzmann equation, and you know I quoted around about 10 to the 13 and 10 to the minus 13 millibars. So you know the pressure, we know the volume. We would use actually, what's his name? Avogadro number when you're calculating all of this into it, you're factoring into it. But for my suspicious feeling that it may not be those, what our gentleman or lady said. But clouds are divided into 4 different types. So you have dense cloud, you have I can't remember what the other 3 are because I specialize in dense clouds, yeah? And one of the clouds has the lowest number of molecules, recorded, yeah?
Mm-hmm. Muchas gracias. Thank you very much. Adrian, do you want to say something? Okay, it seems not. Well, if it's not the case, then let's say thank you again to Dr. Sohan Jeeta.
Thanks.
And well, let's thank him again.
Yeah. Let me give you one of these. These are just happened, one of our projects. Okay, pass it over.